Welcome back to Intro Stats. This video is going to walk through doing a z-test in Excel. There won't be a video for SPSS for this because to do it you would have to write code in SPSS and we really don't focus on that. So I'm going to show you how to do it in Excel, and then for the remaining test I'll show you how to do them in Excel and how to do them in SPSS if you needed that. So here we have some data. It's very similar to the data that we used from the PowerPoint, and you see that I've already put in some of the information. So in column A, we actually have the SAT scores, and we're going to go ahead and calculate the mean and the standard deviation. You'll see that all of that information is equal to what we had in the PowerPoint. So when I walk through this, the calculations should give us the same outcome. I've pulled the population average and the population standard deviation from the PowerPoint. I also have noted our alpha level and I've noted our Z critical, which based on the one tell test with an alpha of 0.05 is positive 1.65, and we already talked about that in the lecture itself. So first we're going to count how many scores we have, make sure that we actually have 100, which would then make us match with the lecture. And if we look at that, we find that there are in fact 100. We could also double check that we're not missing any scores down at the end of this column, and they do in fact stop at A101. So there are 100 scores. For the average or the mean, we could take the total number, we could get the sigma x by adding or summing all the scores together for A2 through A101. In this case though, we're going to use the shortcut because we've already talked about where is that score coming from, what does that score mean, and as we move forward, we want to make better use of our time, and you should constantly be kind of keeping that in the back of your mind. I'll ask you conceptual questions about it, but from a practical standpoint, it's faster to do it this way. So we're going to say, what is the average of those scores? We find that the average or the mean is 532, again, consistent with what we saw in the PowerPoint. Standard deviation, we're doing the standard deviation of a sample, so we're going to do dot S and A2 to A101. So we find that the standard deviation is 21.2. Again, consistent with what we saw before. So our effect is going to be the difference between these two means. So how large is the difference between the sample that we have and the population? That should be 4. That's going to ultimately become our numerator for Z obtained. And then our denominator, the error term, standard error of the mean. And you'll note that in a lot of videos, I don't actually go through the time to put this symbol for standard error of the mean. And in fact, the symbol for standard error of the mean changes depending on the test that we do. So often when I'm working in Excel, I just use the abbreviation SEM for standard error of the mean, and I use that abbreviation for every test. So it doesn't matter if I'm doing standard error of the mean for one sample Z, one sample T, independent T, ANOVA, I will use that to indicate the error term. So I'm going to say equals, and that standard error of the mean in this case is equal to the standard deviation of the population divided by the square root of the sample size. And we find that that is 2.21. So then when we go to do Z obtained, it is simply this effect divided by the error term, and we find that our Z obtained is 1.809955. Now if I wanted to round that to 2 decimal places, I can go in, right click, go to Format Cells, and I can specify under number that I want this to be a number, and I can specify 2 decimal places, I can specify 4 decimal places. On some level, keeping those additional 2 decimal places wouldn't make any difference in our calculations moving forward, and in fact we don't use Z obtained to make any calculations. The only thing we use it for is for the decision, and it won't make a difference either way. But keep in mind, typically you would keep 4 decimal places and then report 2 decimal places whenever you are doing this. So for consistency, we're going to go ahead and keep 4. Now that gives us the obtained. We could also look at what is the effect size. And so here we want to say what is the effect, which is at C9, that's the numerator. So again, that's the difference between the population mean and the group mean. What is the effect divided by or relative to the variability in the population? So the standard deviation. And we find that that is 0.180995, which is consistent with what we reported in the PowerPoint. Again, if you want to make sure it's consistent, you can right click, go into format cell, and specify that you want 4 decimal places. Now, the last part of this is making the decision. And really to make the decision, we're going to look at Z obtained relative to Z critical. It can be helpful to actually visually draw out the distribution, create your cutoff, and then put the point on that distribution to say, where did this Z obtained fall relative to Z critical, the same way that you saw in the PowerPoint itself. But we can see from this that our Z obtained is greater than, rarer than our Z critical. And again, when we say greater than, that's a little too specific sometimes, because if we have, for instance, a 2-tailed test, it could be greater than or less than. If we have a 1-tailed test that's in the negative direction, greater than actually would be not significant because it should be less than. So really what we're saying is in absolute terms, right? So if we did absolute values, in absolute value terms, Z obtained is larger in magnitude compared to Z critical. So it is beyond, it is more extreme. And importantly, with a 1-tailed test, it is more extreme in the correct direction. Because it could be that we end up with negative 1.81, for instance. Well, technically, we have failed to reject the null. We believe that they would do better, and in fact, it turns out that the individuals did worse compared to the population. And so because of that, we would fail to reject the null. And sometimes we can talk about that as a type 3 error. If we make a mistake or we have a hypothesis that is not supported by the data, but in fact we would have found a significant difference if we had looked in the other direction. Individuals will talk about that as a type 3 error. The one last thing that we could do, and we really haven't talked about this before, and I'll talk about it more with the t-test, is you can create confidence intervals around the mean. And what this tells us is if we did this again, what range of values would that likely fall within? And so you can do a lower limit and you can do an upper limit. And for these two, what we're really going to do is say, all right, what was the mean? And if I subtract Z critical times the standard error of the mean, that then gives me the lower estimate of where would this likely fall if we were to collect data again. And then for the upper limit, it's actually very similar code. And the only real difference is for the upper limit, we are going to add and so what we're really saying is if we look at the variability within our data, the error that's within our data, especially the error within the sampling distribution, if I take my Z critical, multiply it by that error term, we can create cutoffs on the lower and upper limit. So if we went and collected another sample of data, we would expect that their mean wouldn't fall exactly at 532, but it would fall somewhere between 528.5 535.3535 and 535.6465. Importantly, we thought that the sample was going to score better than the population. And if we look at, I'm going to change colors to note the contrast. If we look at the population and we look at this lower sample limit, we find that the lower limit is still higher than the population average. So this would suggest that our sample is significantly different from the population, and if we got a new sample, then we would still find that WT students are performing better, because even if their score was lower, it probably wouldn't be below 528.3535. So those types of things can be useful, and we'll talk more about the confidence intervals conceptually in the video for the t-test.